Ramakant sir?
Yes, sir. Sir, good evening.
Sir?
Madam, 1 minute.
Yes, sir. Yeah.
Hemant, sir?
Yes, I'm here, sir. Yeah.
Sir. Okay. Jayashree, madam.
Okay, sir.
Please.
Good evening, my dear participants. I welcome you all for the 4th day International FDP on Data Science. Now I welcome Hemant sir to continue the session. I request Hemant sir to start the session. Over to you, sir.
Yes, madam. All right. So I'm audible to all?
Yes, sir.
Yeah. Thank you. Okay.
Yeah.
So let me continue with the yesterday's session. I'll try to share the screen. All right. So in the previous session, we had a discussion on a linear regression, which is one of the simplest algorithms. All right. Basically, in the today's sessions, we'll be seeing some of the other important algorithms, and I'll also quickly run through this Jupyter notebooks, so that already have compiled. Could be one of the TensorFlow example, and also some of the algorithms like k-means algorithm, clustering algorithms, and then classification algorithms by considering some data set. Okay, this was the example that I took. We have a website here, so setosa.io, basically. That is one of the a really good website. So I have also shared a link, the PPT with the host, so you can also get the PPT of this session. You can visit this particular website. You can see how this linear regression actually works. Seeing some animations. All right. Yeah. So coming to this one, I said that this is basically the best fit line, and then we have this MSE. MSE stands for, it is a mean square error. That is the evaluation metrics for this linear regression. We also have this mean absolute error. So basically that is used to reduce the weights that we're actually giving to this values, the errors. All right. And then we also have this share this insight, saying that grade is equal to 65 plus 1.5 into hours. You start inputting the hours value, and then you actually get the grade value. Let's say, for example, if this is the predicted line or the predicted model, let's say that a student is studying for 10 hours, maybe, sorry, 10.5 hours. So then what might be the grade you will get? It is around 78 or 79 marks, something like that, isn't it? Right. So that is what this particular equation is telling. Now coming to this, R squared is basically another statistical measure. So that usually says the goodness of your model, that usually varies between 0 to 1. Okay. So if the value is above 0.50, then your model is best model, which predicts the target correctly, right, to some extent. All right. Yeah. So coming to this logistic regression, which is one of the supervised machine learning algorithm. So one of the very fundamental algorithm that everybody has to know. Coming to this logistic regression, as I told you that this is basically the categorical algorithm. It means that it considers the categorical data. Take an example of the email, as I told you that ham or spam. So emails that is automatically going to this inbox, and then some emails which is automatically going to your spam box. So that is basically a text processing mechanism internally using this text classification algorithms, all right? And then trying to predict whether a customer will buy a product or will not buy a product, given the age and the salary of a person, all right? So I have taken one example here. So let us try to understand how this logistic regression is based on linear regression, all right? So I've taken one example here, probability of getting infected given age. So this is basically the probability problem. It means that the probability has to range between 0 and 1, all right? So we have taken this particular animations here. So beta naught and beta 1. So we are giving, n number of values, different values in different iterations. And then this is basically the S curve, what we call it as a sigmoid curve. We'll try to understand what is the sigmoid curve or S curve, all right? The problem, the question that I have taken is probability of getting infected given age. So coming to this part, so in the y-axis, I've taken this infection, and in the x-axis, I've taken this age. Age ranges from 20 to 55, and then infection, the values from 0 to 2.5. All right, so let's try to solve this using linear regression. Basically, I'm trying to solve this problem using linear regression. And let's see what is the problem that we see when I try to solve this particular problem using this linear regression. All right, so coming to this one, so the age is given here, which is 20 between 55. So the range is given here, and then I will have to note the point here. The P is a probability which actually varies from 0 to 1. And then we know that I'm trying to solve using linear regression. It means the straight line, which is basically y is equal to beta naught plus beta 1 into x1. Okay, I've taken only one independent variable here, so that is the reason it only showing x1 here. Okay, so which is age, right? You can also consider some other independent variables. Okay, infection also depends on other variables too, but for simplicity I've taken only one x1 here. You can also say something like x2, x3, x4, etc. All right, now the case one is I've taken some random values for this beta naught, and then what is it, the age. So the thing is beta naught is equal to minus 1.700, and then this is beta 1, some typos happen. Beta 1 is equal to 0.064, and the age is 35 years. All right, so I wanted to predict y of p is equal to 1 given age. Okay, so we have given the age, which is 35, and we'll have to say whether the person will get infected or not. By just plugging in these values, we have this minus 1.700 plus 0.066 into age, which is basically this x1, and then we have this 35 here. So by doing this, substituting this value, we get 0.54. It means that 0.54%, 50% of chances are of getting infected if the age is 35 years. Okay, and then we have given two other ages, which is 25 and 45. So for the age 25, so let's see now, y of p is equal to 1 given age. What is the age now? It is 25, and then let's try to plug in this values, which is minus 1.700 plus 0.064 into 25, and we are basically getting minus 0.09. So remember that this is basically the probability problem. It means that it has to range between 0 and 1. It has to not go below 0, and then it should not go above 1, right? So we have taken this 45 now. When I substitute this 45 to the same equation, I do get 1.20. It is going above 1. So when I try to plot this particular graph, I'm actually seeing this line, regression line, a straight line, something like this. So for the age 45, it is going above 1, all right? And for age 25, it is going below 0. If you just extend this regression line, you'll be able to see that you are actually getting the negative values. But it is basically the probability problem. It has to range between 0 and 1. Now the thing is, how do you bring that value between 0 and 1? That's the thing we'll have to do it here. So some kind of engineering thing we'll have to apply in such a way that we'll have to get the value between 0 and 1. So let's chop off this line which is going above 1 to 1 and then below 0 to 0. Okay, so how do you do that? That's basically applying this logistic regression. So we thought of solving this problem using this linear regression, and we got to see that the values were actually going above 1 and then below 0, which is not acceptable, isn't it? That is what I'm saying here. Observe the plots, predictions are going above 1 and then below 0, which is not at all acceptable, because this is the categorical 1. It has to be 0 or 1, getting infected or not getting infected, right? So now coming to this one, let me try to do some engineering to this particular one. So what is the thing that I'm doing here? So the value has to be greater than 0. It has to be greater than or equal to 0. For that, what we can do, just try to apply this simple mathematics, right? I've taken the same linear regression equation, which is basically beta naught plus beta 1 into x 1, or x, simply x, and then I'm taking this exponent for that. You know that if you're considering this exponent, so that's basically the positive value, right? So probability of x is equal to exponent of taking exponent to that particular equation. It is always a positive 1. It means that it will be always greater than or equal to 0. So I've satisfied one condition here, which is basically p greater than or equal to 0. And then I wanted to satisfy the second condition, which is basically p less than or equal to 1. I'll have to bring that value below 1 or equal to 1. So what we can do now? So let me take this equation, exponent of beta naught plus beta 1 into x divided by one number greater than that. If you just divide any number greater than one number to that, so you'll be getting below that particular number, isn't it? So exponent of beta naught plus beta 1 into x divided by 1 plus exponent of beta naught plus beta 1 into x. If you just add this 1 to this particular denominator, then obviously it has to be below 1 or equal to 1, right? So and then doing some mathematical operations here, bringing this to your left hand side, and then we have this p of x into 1 plus exponent of beta naught plus beta 1 into x, which is equal to exponent of beta naught plus beta 1 into x. And then so just taking the common out of it, we have this exponent of beta naught plus beta 1 into x minus p of x exponent of beta naught plus beta 1 into x. So 1 minus p of x is the common that we have taken out, exponent of beta naught plus beta 1 into x, right? And then bringing this to your left hand side, we have this p of x divided by 1 minus p of x, which is equal to exponent of beta naught plus beta 1 into x. So basically what we are seeing that in the left hand side is called as the logit function. Okay, so the logit function in statistics says that so the probability of event happening divided by the event not happening, which is basically p of x divided by 1 minus p of x. That is called as the logit function, which is equal to exponent of beta naught plus beta 1 into x. Now I just wanted to prove that this logistic regression is based on linear regression. It means that so we'll have to get that linear regression equation. How do you get that linear regression equation? By just taking this logarithm on both sides. If you just take this logarithm, take natural logarithm on both sides. We know that in mathematics, logarithm and exponent are always opposite to each other, isn't it? So that's the reason I'm taking this log of p divided by 1 minus p, which is equal to, when I take this logarithm to this exponent, it gets cancelled, and we have this beta naught plus beta 1 into x. And finally, we have in the right hand side, which is beta naught plus beta 1 into x, which is what we say it as equal to y is equal to beta naught plus beta 1 into x. So this is basically we are trying to prove that this particular logistic regression is based on linear regression, saying that, okay, doing some mathematical operations, we say that y is equal to, now it is equal to beta naught plus beta 1 into x. Now we have this right hand side of this particular equation, and we also have this equation, which are both are same, and we say that this logistic regression is completely based on linear regression. So once we do this kind of, a little bit of a mathematical operation, and then we could see that we could able to bring that value to 1 and then to 0. So previously it was going above 1 and then below 0. Then we could able to see that. So we were able to bring that particular value, that particular graph, which was going above 1 to 1 and then below 0 to 0. And as you can see here, this is basically the S curve. Okay, so S curve also called as the sigmoid curve. All right, so we have an equation for that. What is that equation for logistic regression? It is basically the p of x is equal to exponent of beta naught plus beta 1 into x divided by 1 plus exponent of beta naught plus beta 1 into x. This is basically called as the sigmoid equation or logistic equation, right? Logistic regression. Why do we call it as a logistic regression? Logistic regression because we are using this logit function to prove that it is based on linear regression. That is the reason it is called as logistic regression. All right. So coming to this one, so we have this p of x is equal to exponent of beta naught plus beta 1 into x divided by 1 plus exponent of beta naught plus beta 1 into x, and then divide both numerator and denominator by exponent of beta naught plus beta 1 into x, and then finally we get 1 by 1 plus exponent of minus beta naught plus beta 1 into x. So whenever you divide this both numerator and denominator by this exponent of beta naught plus beta 1 into x, all right, and then substituting this value, the exponent value, we do get p of x is equal to 1 by 1 plus exponent of minus z, referred to as sigmoid equations, where z is equal to, we're just substituting that value, okay, z is equal to beta naught plus beta 1 into x. So just remember this particular equation, because this is an equation that is also used in this, a neural network. Sometimes we use a function called sigmoid activation function, okay, just to activate your neural network, right? So this is how we actually try to derive this equation called sigmoid equations. All right, so this equation is particularly used in this neural network and then in the traditional machine learning algorithm. All right, so this is how we are going to prove that linear regression, logistic regression is based on linear regression. All right, now this is basically the classification, the supervised concept, so which works with the categorical data. So we observe that this linear regression will not give us the desired result using this categorical data. All right, so that is the reason we are going with this logistic regression. Okay, now coming to this one. So when it comes to this classification, so we are done with the regression part. When we are done with this linear regression, we also see some of the evaluation metrics like MSE and then MAE, mean absolute error, mean square error, and then R squared. All right. Now that is basically the evaluation metrics for linear regression. But now for this logistic regression, or generally speaking for the classification, I know you people have gone through this concepts like the accuracy, recall, precisions, and effort score. Okay, now we will try to look into this concept like what is accuracy, recall, precisions, effort score. When we have this accuracy, why it is required to have this recall, and then precisions, and then effort score. We'll try to look into that by taking some couple of examples. All right, now coming to this one. So basically this is the splitting part. We'll try to see that later. Coming to this model evaluations, I've taken one image here, basically the dog image, which I say it as a test image, and we already have a model which is already trained. All right, so we have a model which is already trained, and then this test image is given as an input to this particular trained model, and this model is saying it is dog, which is basically what we call it as a prediction. All right, the actual one is also dog. It means that the actual label is also dog, and the predicted one is also dog. Just we are trying to compare the predicted one with the actual one. So dog is equal to dog. So which says that of course it is correct because the model is also saying it is dog and the actual label is also dog. The both are correct, isn't it? So your model is predicting the correct label. All right. Now coming to this part. Now the test image is basically the dog, and then it is saying that it is cat. But the actual one is dog. Dog is equal to cat. No, the prediction is wrong. All right. This is how we basically evaluate this classification model. Right. This is one example, very simple example that I have taken. Let us see some more example in the same way. Now coming to this accuracy, let's say that accuracy in classification problems is the number of correct predictions made by the model divided by the total number of predictions. It means that number of correct predictions divided by total number of predictions. What does it mean actually? So let's see. Let's take an example that you have 100 dogs and cats images. Out of hundreds dogs and cats images, 80% of the data have been correctly or rightly predicted by your model. If that is the case, what is the accuracy of your model? 80% is the accuracy of your model, isn't it? So that is what this accuracy is all about. Number of correct predictions divided by the total number of predictions. Now coming to this, we'll see a problem with accuracy. This is very important for the perspective of this recall and then precisions. We have seen why this accuracy is very much required. We have learned that, okay, what is the accuracy of a model? Whenever you train any model, we usually see this, point. We usually directly ask that, what is the accuracy of your model? Isn't it? But we are least bothered about this other metrics like recall and then precisions. We are not knowing that why this recall, why this precisions are being used. So which is also very important, which also plays a very important role is in the classification metrics. All right. So we have a concept called imbalanced classification. So when we actually go with this kind of model evaluations, we also consider this imbalanced classification. What is this imbalanced classification? I've taken one example. Accuracy is not a good choice with unbalanced classes. What do you mean by unbalanced classes? I've taken this COVID example, only the current example. Imagine that we have 90 rows of negative COVID-19 patients and 10 rows of positive COVID-19 patients. That is a base data set that you have. So out of 100 records, okay, of people, 90 rows of negative COVID-19 patients and then 10 rows of positive COVID-19 patients, right? Now, let's say that you have taken this data set and you have trained your model, a classification model. I don't know what kind of algorithm you're using, but you have actually trained your model. All right. When you're done with that, whenever you take a new data set or an unseen data set, or whenever a new person approaches you and then you wanted to get tested by your model, then you simply give all the symptoms of that particular person, and then your model always says that is negative, isn't it? It means that, so the model has taken more number of negative COVID-19 patients rather than the equal number of classes. We would have taken like 50% of negative COVID-19 patients and 50% of positive COVID-19 patients in our data set. But the maximum of is basically the negative COVID-19 patient data set. All right. So this will create a problem of imbalanced classification, and then we end up with the a bad model. It says that, so even though you have trained the model, even though the patient is positive patient, it always says negative one. All right. So the ulta of this is, if you have taken this 90 rows of positive COVID-19 patients and 10 rows of negative COVID-19 patients, your model has learned more of this positive one. And then whenever a negative patient, symptoms is given to this particular model, it always says it is positive, isn't it? It means that you're always getting this really good accuracy, which is a false accuracy, right? We should not consider this kind of data set that we call it as imbalanced classification. We'll have to overcome this kind of problem in the real world, projects. All right. So how do you actually overcome this? So with the usage of this recall and then precisions. But before that, let's take an example of this confusion matrix, which is very important to understand this different concept of, confusion matrix or terms of confusion matrix. Now we have this actual case, which is the positive one. So let's say that, so the left hand side is basically the positive one. The actual one is positive and your model has predicted positive. The actual one is positive and then your model is saying it is negative, right? And then the actual one is negative, okay, and then your model is saying it is positive. The actual one is negative and your model is also saying it is negative. So let's quickly see this confusion matrix. Now we have the true condition, we have the predicted conditions here. So condition is positive, 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 it is always true positive, positive, and then it is predicted as negative. This is the dangerous case, which is very important here. So this is the second case that I have taken here. So the condition is basically the positive one, and then the model is saying is negative one. This is the dangerous one, what we call it as a false negative, type 2 error. All right. So this is dangerous because once the person is identified as a negative, even though he is the positive one, and then he can happily go to the public and then he can start spreading the disease. That should not happen to us, isn't it? So that's basically the problem that is always associated with this kind of false negative, that we call it as type 2 error. And the next one is negative, and then it is being predicted as positive, what we call it as a false positive. This is somewhat okay for us to some extent, because we may go with the second test. Okay, the negative patient is now the positive one in the first test. Maybe the second test you will be predicted as the negative one. That's somehow okay for us, right? So this is basically the false positive, also called as type 1 error. And then we have this negative, which is true negative, TM. So these are the short term that you'll have to remember: TP and then FN, FP and then TN. This is basically the confusion matrix taking this COVID-19 different cases and the model predicted one. All right, I will quickly jump into this precisions and recall. As I told you that there is always a problem with this accuracy when we have this imbalanced classification or unbalanced classes. All right, so to just overcome that, to handle this false positive, we take this precisions. Precisions is equal to true positive divided by true positive plus false positive. We try to handle this false positive, which is type 1 error, and then to handle this type 2 error, false negative, we go with this recall. Recall is equal to true positive divided by true positive plus false negative, which will not be handled by your accuracy measure. All right, so which is very important to us. Okay, so that's very important. So coming to this accuracy, precisions and recall. So coming to this F measure or F score. So basically, if you wanted to combine this precisions and recall into single measure, so that's basically this F score or F measure. So 2 into precisions into recall divided by precisions plus recall will give us both precisions and recalls into single measure value. All right, so what basically precision says, appropriate when minimizing false positives the focus. Always we try to minimize the false positive in precisions, and coming to this recall, minimizing false negatives is the focus. Just remember this keywords: minimizing false negatives, minimizing false positives is the job of this precisions and recalls. Combining these two, we have this F measure or F score. That's very important. All right, yeah. Now coming to this one, the last one, which is the unsupervised MN. So unsupervised MN is basically this one that I've taken is K-means clustering algorithm. So I think the animation is not properly visible. So let me quickly go with the Google Slides just to show this one. Let me try to stop sharing the screen for just 1 minute. I'll quickly open this in Google Slides. Okay. All right. All right, so let me quickly share the screen now. So I hope you can see the screen.
Yes, sir.
Thank you. All right. So this is basically the unsupervised one. As I told you that in the unsupervised one, we'll be not having the target concept or the output variable, isn't it? So that's basically finding the hidden patterns and then trying to cluster the similar items or similar data points, right? So as you can see in this particular animations, what I've done is that I've taken this three colors here, the red, blue, and the green, and then you can also see these stars moving from one place to another place, and then on the top you can see the k-means iterations. It is iterating for n number of times, maybe for 10 times it is iterating, isn't it? So this is basically the k-means algorithm, what actually it is trying to do. So the thing is, when we have these points like this, we wanted to group the similar points. As you can see here, when the stars are moving, the red color is getting changed to blue color, and blue color are getting changed to green color, and then green color is getting changed to blue color, something like that, isn't it? So it means that we are grouping the similar data points. How we are actually doing that? So this is basically, I'll not go through the steps, but you can see this figure and then we can understand the things. So basically we take the centroid, okay, initially a random centroid, and then we try to update the centroid in every iterations. It means that we take a point, random point as a centroid, and we'll try to bring those points which is very close to the centroid, and then we'll calculate the mean of that particular centroid or a cluster, okay? And then when we calculate that mean, centroid itself is a mean, and then we try to update that centroid. So basically what you're seeing, the star, is the centroid, which is moving from one place to another. So why it is actually moving? Basically, we are calculating the mean of this cluster, and then we are trying to update the things. And then as in when this particular centroid is moving from one place to another place, so the points which are very close to the centroids are actually getting changed. Okay, it means that the color of those points are actually getting changed. Now, how do you actually measure the distance between the centroid and the point? So you may go with different measures. Basically, in the context of data science or machine learning, we'll be using this Minkowski distance. Okay, basically, if people have read this data mining concepts, you'll be knowing this Minkowski distance, and then Euclidean distance is one thing that we'll be using. So that is what we see it here. So if you wanted to measure the distance between the centroid and the point, we always consider the Euclidean distance or Minkowski distance. We also have this Manhattan distance. It is all depending on you that how you actually choose these distances between this centroid and the points. All right. So finally, when everything is done, when you see that all the clusters are grouped perfectly, then we stop that particular iterations. As you can see here, until no change, we have this particular equation, which is basically the distance matrix, which is Euclidean distance, q1 minus p1 the whole square plus q2 minus p2 the whole square in general. So square root of summation I is equal to 1 to n, which is q1 ui minus pi the whole square, right? So
Can
this
you
is
explain the equation, sir?
Excuse me. Okay, pardon me. Sorry.
Yeah.
So
the equation.
Yeah. So basically, this is the Euclidean, just a coordinate. We'll have to consider the coordinates, and then we'll have to measure these points basically. So when we actually plot this particular graph, we take the coordinate, just the simple mathematics that we had actually, how we actually subtract this x1 minus y1 the whole square plus x2 minus y2 the whole square. In that way, we'll have to compute.
What is exactly q and p here?
So that's basically the x and y point.
Okay, sure.
Yeah.
This equation is similar to information retrieval system contains that this equation is there.
Yeah, right.
Yeah, so that one I am asking.
Yes. So that's basically the thing that we do it in, K-means algorithm. So K stands for number of clusters. The thing is, you'll have to decide. The thing is, people do always get confused that when we have these points, how many clusters you are going to form. So that is always the question that always arises in your mind. So do we have that idea that how many clusters that you're going to form? How do you actually take the number of clusters? That is very important. Okay, the thing is, in the data science or in the machine learning, we have a concept called elbow method, which is very important. I'll just show you that elbow method. So elbow method is basically the method that is used to know how actually we will consider this elbow method. All right, I'm not going to show it completely. Basically, that's the method that we usually use. I request that you'll have to explore this method, elbow method, runs K-means clustering algorithm on the data set for range of values for K, say from, you'll have to give that programmatically. You'll have to pass those values from 1 to 10, and then for each value of K, computes an average score for all the clusters. This is basically the elbow method. So if you just see this, the images, so this is basically the elbow method. So the thing is, this is the optimal point, so that we say that, okay, this is basically the number of clusters that we'll have to consider. Elbow method showing the optimal K. Now how we'll have to take, this is in the shape of elbow, isn't it? So that's the reason that you're not going to decide simply that this is a number of clusters that you'll have to consider. So you'll have to go take this elbow method and decide how many clusters we will have to consider, which is basically 3 in this case, isn't it? So that's basically what we do in K-means clustering algorithms, considering this elbow method programmatically. All right. So yes, let me stop sharing the screen. Let me go back to the slide now again. Yeah. So that's it. The thing is, that's the theoretical part of this. Is if you wanted to master yourself with this data science, as I told you that you'll have to concentrate on this Venn diagram, data science Venn diagram. You'll have to look into the concept of this linear algebra is very important. Statistics is very important. You should know the concept. Basic statistics is very important, and also, as a researcher, you'll have to know the different, statistical concepts like sampling. Concepts, and then what is it, the different basic concepts like standard deviations, variance, bias and variance, bias entry, variance trade-off. So all this basic statistical concept is very important, right? Machine learning is all about the applied statistics, and then bit of linear algebra. I suggest that you should not go and then dive directly into this linear algebra. First learn that linear algebra and then going to this statistics. No, it's not like that. So just start with the machine learning, start with the algorithm, but try to understand what's actually happening behind the scenes. That could be the statistics, that could be linear algebra that is used in every kind of algorithm. Right. So in that way, we'll have to go with the thing. Some of the websites that I usually prefer is like Machine Learning Mastery by Jason, one of the really good website that you can usually refer, that Machine Learning Mastery towards data science. So you can just contribute many articles if you're really well versed with some of the machine learning algorithms. Yes, of course, you can go with that, towards data science, websites where people are actually contributing many articles to that. And then pythonprogramming.net, right? That is also one of the really good website. Analytics India, and then for documentation to understand this machine learning algorithm, scikit-learn, which is one of the frameworks that we use to learn with this traditional machine learning algorithms. All right, so you can just go to that. And then we also have this tensorflow.org. TensorFlow is an open source framework that is by Google. You can also look into that TensorFlow. And then the Keras is basically which is what we say it as TensorFlow is built on top of this Keras. And then we also have this Anaconda distribution just to go with this kind of tools. And then if you are running this neural networks and other things, take the help of this collab.research.org, and then you could able to explore many predefined notebooks, and you can also start running your machine learning algorithms on GPUs and TPUs. And then for data sets, Kaggle, you already know that Kaggle is one of the famous website and UC repository. All right. And then for any courses that you wanted to do, to take this, to become a certified one, to take exams on data science. So one of the website is IBAC, which is International Analytical Business International Association of Business Analytics Certification. That is basically one of the website that you can go with the things, right? And then so all this basically the Python libraries that you'll have to learn, like NumPy, Pandas, and then scikit-learn, Matplotlib, TensorFlow, Keras. So and then this Collab, and then all these are basically the tools that we use. And then building your portfolio. You may be a researcher. You might become a data scientist in future. You may be a data science aspirant. The thing is, you'll have to build your profile, which is very important. Start contributing data set to the Kaggle, and then start writing some articles to the Medium. It could be a very simple concept, or it could be a very complicated one. So just try to contribute. Put in your the content in your own words, and then try to contribute to this websites like Quora.com and then Medium. And then once you're done with the projects, so also try to push those projects to this GitHub. GitHub is very important. See, once you wanted to be in the industry, or else being an academician, if you wanted to just improve your credibility or your profile, then you'll have to understand this GitHub things also, which is very important. You'll have to show that to the world that you have done these projects on your own. All right. So this is also a very important skill that you must have, to build data science profile. That's it, the theoretical concept. So you can connect me on. This is my email ID. All right. So, and then personal email ID, and then this is my LinkedIn profile, linkedin.com/in/hemantkumar12, and then this is my phone number 7929776420. You can connect me at any point of time. So I'm always reachable to you all, right? So I hope this is all clear to you all, right? Let me quickly try to share some of the notebooks now. So we'll take another 30 minutes to understand some of the basic algorithms that we have learned already. Let me try to go with this notebooks now. All right.
Can you share your mail ID, sir?
Yeah, sure. I'll be sharing it.
Last slide.
Yeah, I'll do it. Yeah. I hope you can see that email ID. All right. Okay. So this is my email ID. So at the end, I'll also share the email ID. We're running out of the time. We quickly run through this Jupyter notebooks. I have 3 or 4 notebooks. Let me quickly go with the notebooks, and we'll try to see how these algorithms are actually working. And if time permits, I'll also take this particular concept, which is the TensorFlow example. All right. Okay. By running this neural network, I hope you have done with this neural network in the previous sessions. All right. Okay. Let me quickly open Jupyter notebook, and we'll see some of the programs now.
Excuse me.
Yes, sir.
Sir, this is Dr. Mooninder Singh from Thapar Institute of Engineering and Technology, Patiala. I have one small query. Can I please ask?
Yeah, please, sir. Please.
Sir, when we are classifying data, especially related to physiological signals, for example, let us take into consideration EEG signals. So the data in that case is highly singular in nature, though it might be due to different stimulus. But if we perform simple correlation, then we will see that the data is singular in nature. So will it be possible to analyze such type of data using K type of technique?
You mean K type of technique?
I mean, sir, the clusters that we were discussing just right now.
Okay.
So in that case, will it be possible to analyze the data using clusters?
Can we discuss this maybe at the end of this session, sir? probably.
Yes,
Yeah.
definitely.
Otherwise, we can have a call regarding this. Like I'll have a complete details regarding this. So we'll try to discuss that.
Well,
All
well, I
right?
think so. You understood my question, especially in case when the data is of very low amplitude and it is of
Yes,
very
yes, I understood.
frequency.
Understood. So
Okay,
we'll discuss it, sir. We'll discuss it. I
okay,
think it will take some time, right? So let me quickly show some examples. I think I left it with only 30 minutes. Okay, we'll try to discuss it through the mail or through the call otherwise, right? I think I hope you can see the screen, right? Can you see this window, the Jupyter Notebook?
Yes, sir.
Yes, sir. Sir.
Okay, so all right. The thing is, this is very simple example that I've taken here to understand this, algorithms, regression algorithms. Basically, I'm using some model like stat model here, so which is what that I've already typed in. So there are some of the libraries that is very important here. Libraries like NumPy, so numerical pi, which is very important just to do some scientific calculations. And then we have this pandas just to create this 2D matrices. And then we have this stats model.api. All this as and then as NP, PD, and then SMPLT are basically the alias name for this packages. NumPy as NP, and then pandas as PD, and then statsmodel.api as SM, and then matplotlib.pyplot is basically the class, and then as PLT. And then on top of this matplotlib, I also request you to explore this Seaborn. Basically, the Seaborn is built on top of this matplotlib. So we have many options in Seaborn just to have this graphical representations of this analysis. All right, and then we are setting this SNS dot Seaborn. So basically we are trying to override. So we have a concept of overriding in every programming languages, isn't it? So since I'm using this matplotlib and also Seaborn, so I'm trying to actually override this by putting this method which is dot set. So I'm just taking the present working directory, which is basically this my present working directory is this one. So on the desktop I've created some kind of folder. All right, it is taking some time basically. Okay, so and then so I've taken this simple linear regression.csv. So that's basically all right. So let me quickly run this. So now the thing is, on the desktop I've created this bits folder. In the bits folder I have this data set and then this program files, and then I'm making use of this read CSV function. So basically this pandas PD dot read CSV, and then I'm reading this particular CSV file. All right, and then I'm trying to print this data. All right, okay, so what we see here is this one. So this is what the CSV file looks like, the SAT score and the GPA. So we know that in states, in the countries like USA, we do consider this assessment test, scholastic assessments test, just to know that whether this student is eligible to take up this entrance exams or degrees, right? And then grade point average. So based on the stat score, we are actually predicting this grade point average. Basically, we have this 84 rows and then 2 columns, all are numerical one. So basically regression works with numerical data. And then this is the one that I have taken here. Very simple example. Remember that I'm not going to make use of this Python scikit-learn library here. So that's basically will be explored in the next notebook. What I'm trying to do here is that just to know how actually this works with the stat model. So that will be done in this particular notebook here. So and then I'm trying to check the shape of this 84 rows and then 2 columns, and then trying to describe this. So when you try to describe this, we do get this different statistical measures here. All right, so mean, standard deviations, minimum, maximum, 25% of the values which comes in between this, 50%, 75%, something like that, right? And then I'm checking whether this data is actually having any missing values. All right, so I'm using a function called data.isNull. isNull is basically this value or the function which will give us something like this: false, false, false. It says that so no missing values we have on this particular data set. If you have any missing values, you'll have to go with the pre-processing one. All right, and then the thing is, you will have to assign this, what we call it as the y and the x variable. All right, we wanted to predict GPA, and then we have this SAT score. When we have the SAT score, we'll have to predict the GPA. So we have this y variable here, or y variable data of GPA. I'm trying to assign this GPA to this y variable, and then I've taken this x1. I'll tell you why I've taken this x1. x1 is equal to data of SAT score. So x1 is basically the independent variable, and then y is basically the dependent one. All right, so let me try to quickly run this, and then let me try to perform this EDA, exploratory data analysis. All right, so for that I've taken this PLT. So in this example, I'm not considering this SNS, but I'm considering this PLT, which is matplotlib, basically that is used to perform this analysis part. All right, now I've taken this PLT.scatterplot. I'm trying to plot this scatter plot by passing this two parameters, which is x1 and then y, and then I am taking this function called xlabel. Okay, X label, I am naming it as SAT, which is the independent part, and the Y label, which is basically the GPA part, the dependent part. And then I'm trying to add some constant. This is very much required because whenever you consider these equations like y is equal to beta naught plus beta 1 into x, we're trying to add a constant for this particular variable, which is x1. So that is done by using this stat model SM. X is equal to sm dot add constant of x1, and then result is equal to sm dot OLS. What is this OLS? Is basically, that is the method that I'm going to use. OLS is basically the ordinary least square method. Least square, it means that, remember the concept of linear regression, it means that you'll have to always reduce or minimize the distance between the actual point and the point on the line. So that will be done by this model called OLS model. All right, so this is very important to know. Just try to explore what is that OLS. OLS stands for ordinary least square. As the method itself says, least square. We'll have to get the least square, and we'll have to pass in y comma x. We are passing two parameters to this, which is y and then x, and then finally we'll have to fit that model. All right, so fitting the model says that you're actually trying to fit a line, a best fit line, to the points that you have actually taken. All right, imagine that you have plotted this points, okay, the SAT score and the GPA after taking that, and then you're trying to fit a line. Just imagine the grade point predictions that had done that in the theoretical concept. We're trying to fit a line, so it means that it will take n number of iterations, and it will come out of a best fitting line. It's what we call it as a model or a regression line. All right, and then I'm trying to consider this results dot summary. We'll see that summary. What is that summary? We'll have to understand the summary part, which is very important. And then I'm taking this PLT dot scatter of x1 comma y. So we are passing this x1 comma y. So basically I'm trying to plot that. So I'll have to separate this any of, okay, so I'll have to put this in a separate cell. But remember that I'm trying to plot these points using this scatter function, which is scatter of x1 comma y. And then we know that y hat is basically this one. Let me do something like this. Okay, just observe here. So I would have written that previously, but anyhow, so this is a final model, but observe this particular cell here. So when I execute this one, all right, so I'm actually getting this. So remember that. So let me comment this part out. Okay, till here. So let me comment this part. All right. So now the thing is, I've taken this, plt.scat_prof x1 comma y, and then x label is sat, and then GPA is y label. Okay, let us keep this as it is. So I should have written this later, but just observe this one particular summary, results.summary. So you'll have to observe this summary here, which is very important. We know that dependent variable is GPA, and then model is OLS model, least square, ordinary least square method, and the method is basically the least squares. Okay, so I request you to go with the statistical measures, but the very important one, I'll be speaking about this R squared and adjusted R squared. So coming to this R squared, what is this R squared? So we know that in the theoretical concept, so we have a measure called R squared. R squared basically varies from 0 to 1. So if the value of the R squared is above 0.50, then your model is a really good model, right? And then when we have this R squared, why it is required to have this adjusted R squared? So it is very important. This is again a different concept. It will take another 1 hour to go with this R squared and adjusted R squared. So when you consider this R squared, why this R squared is required? That always says the goodness of your model. All right. Now let's imagine that I've taken this independent variable SAT score, and then the dependent variable, which is the GPA. We also said that this is basically the univariate linear regression. Univariate linear regression means what? We have taken only one x and then the y value. Whenever you consider multiple x value, okay, that is called as multiple linear regression or multivariate linear regression. So imagine that. Imagine that. So the GPA will not only dependent on the SAT score, but it also dependent on the prerequisite course that a student has taken previously before taking this examination assessment test, and then the place where in which he's coming from, and then whether it's poor or rich, something like that. So there are so many factors which will influence this GPS in the real world, right? So whenever you consider that, that will become a multivariate linear regression. But when it comes to this R square, there is always a problem with this R square. Let me try to annotate this one. Okay, quickly annotate this one. Annotate. Okay, when you consider this R square, so and then the adjusted R square, as you can see here, adjusted R square is a little lower than this R square. The reason is that, so basically R square increases its value as and when more independent variables are added. What does it mean basically? It means that, imagine that to get GPA, so we said that it is dependent on the SAT score initially, and then sometimes the place and the prerequisite course. Imagine that all these are X variables and this is a Y. Sometimes remember that some of the independent variables are not important. So SAT is very important, of course. A place may not be important. It is not important in some cases, because even the poor student who are coming from the village background are really getting good marks. Okay, it means that even though if you're adding this place as an independent variable to your model, okay, the R square value is increasing. Okay, that should not happen. Okay, that will not tell you the goodness of your model. Okay, as and when you start adding this more number of independent variables, even though it is not at all important, okay, the R squared is increasing. That is a point that you'll have to remember. Just to overcome that problem, okay, we are going with the adjusted R square. In the adjusted R square, we say that whenever the unimportant independent variables are added, okay, to the equation, so that will say that, okay, this is the variable which is not that much important, that you'll have to remove from the particular equation that you have taken, right? So now adjusted R square actually will reduces its value. So whenever the unimportant independent variables are added. So that is very important. So when you are actually trying to model a classifier or regression model, so it is very important to understand whenever you model a regression line, so you will have to think about the variables that you will have to adjusted as square even more, and then F statistics and log likelihood are all basically the statistical measure that you'll have to understand. And then we have this, what is it? Let me stop these annotations now. Okay. And then we also have this, p-value, t-value, and then this standard deviation coefficient. All right. So now we wanted to have a straight line. I've taken this value here, which is beta naught. And then this is the y-intercept 0.2750 and then 0.0017 into x1. All right. So for that, you should see this values here. Can you see this values here? So it is 0.0071, which is the coefficient. And then we have this 0.2750 that have substituted here, which is basically this one. All right. Okay. And then we have this x1. Okay. So whenever you actually done with getting this values, all right, so we'll have to substitute that value and we'll have to try to plot that value in your graph. So this is basically the line that I'm actually trying to get here, right? So yeah, so this is the line that I'm getting here. So basically figure is equal to, after substituting this y hat is basically the line, the predicted one, is equal to 0.0017 into x1 plus 0.2750, which I've already obtained in this summary of the statistics.
Hemant sir?
Yes, madam.
Sorry for the disturbance. Sir, it's time for break now.
Oh, all right. Okay. Yeah, I feel that I can complete this 1 minute. I can complete it.
Okay, sir.
All right. So and then we have this one, and then we have this figure variable. Figure variable is equal to PLT dot. PLT is basically the matplotlib variable. Dot plot of, you will have to pass this x1 and then the y at. Y at is basically the predicted line. So C is basically the color, and line width is basically the 4. And then you are passing different parameters. X label is SAT, and then Y label is GPA. You can see this SAT as this one, the X label, and the Y label is basically the GPA. All right. So when you plot that, you would get this particular graph. So the thing is, once you plot that, so you'll have to think about whether you have really obtained the good best fitting line or not. Okay, so we have different measures for that. We'll have to go with this MSC, and then this R squared is there, and then we have this MAE, the different evaluation metrics. So that's it, basically using this stats model. I'm not going to use any scikit model, but in the next notebook, I'll be using this scikit-learn model. All right, so let's have a quick break for 5 minutes. Thank you.
My dear participants, we'll be back within 5 minutes. Thank you. Hemant sir?
Yes, madam.
Yeah, you can start.
Shall we? Okay, right.
Yes.
All right, so this is what the regression model is all about, using stats model. All right, so the thing is, next I'll quickly take this TensorFlow as in the brochure, maybe in the poster that I've mentioned that TensorFlow examples, right? So let me quickly take this example, which is also linear regression. So this will take, this is basically the 5 days faculty development program. Continuously we'll have to do it. So theoretical concept and the practical. I tried, at least trying to cover this in another 10 minutes. Let's quickly run through this example. So basically this is one project that everybody has to understand. So TensorFlow is basically the open source framework, so that is given by this Google, right? So you can run any kind of machine learning algorithms here. So basically it is having a different structure, slightly different structure when you compare that with this Keras framework already, right? So basically this TensorFlow is built on top of this Keras framework already. Okay, and then coming to this introduction part. So the thing is, we will see this example of basically this is a kind of a project. Okay, so I have taken this parameters now. So the variables: year of sale of the house, the age of the house at the time of sale, distance from city center, number of stores in the locality, the latitude and longitude. All right. So what this machine algorithm should do now? Okay, now coming to this point, input. So we are providing some input here. The house was sold in March 2015, was 29 years old. It has 3 convenience stores nearby. It's 5 kilometers away from the nearest train station and is located exactly at some longitude and latitude. Okay, and then we have this algorithm here. Just imagine this robot as an algorithm, machine learning algorithm, and then we are actually trying to predict the house price, which is the price for this house was probably, it does not say that this is exactly the price of this house, but it says that probably this might be the price of a house, which is $120K, right? So now coming to this, these inputs are given now. We'll have to predict the house price now. So I'm making use of this TensorFlow 2, okay, that you will have to install TensorFlow, latest TensorFlow. I've already installed the TensorFlow, which is pip install TensorFlow, which is the command that is used to install the TensorFlow to your system. All right. So whenever you are running this neural network, I always prefer to go with this collab because we have this GPUs and TPUs there. All right. So I'm just trying to run this on CPU because this is a very simple example that I'm considering. All right. So the thing is, I've already done with the installation. This is basically the installation files that it is showing. So let me quickly go to this part now. It is the packages like pandas is very important, and matplotlib, as I told you that, which is very important to go with this analysis graphical representation. And then we have this TensorFlow as TF, the alias name, and then utilities packages, which is import star says that you're importing all the packages. And then you'll have to split the data into train and the test part, as we have seen it in the theoretical concept. So for that, I'm using this scikit-learn.model selection, which is a class. From that, I'm importing this particular method, which is train test split class. And then we know that, as I told you, that basically this TensorFlow is built on top of this Keras. For that, I'm using this from TensorFlow.keras.models. What is that model I'm using here? This is basically this, what is it? The sequential model, the neural network model that I'm using. So what is that model I'm using here? Sequential model. And then, so that is basically the dense and the dropout. I'll tell you what is the dense and the dropout. Okay, dense is nothing but all the neurons are connected to every other neurons. That is basically the dense neural network. And then the callbacks class, which says that, so I'll tell you what is that. And then from TensorFlow.keras.callbacks, import early stopping and then lambda callback. So basically all these are classes that we are trying to import here. And then we are trying to print that we have imported these statements. Let me quickly run this. Okay, so the thing is libraries are imported. So I'm trying to print that. If I face any problems, I would get that some error, right? If I'm not able to do that. So now coming to this one, I've taken this data.csv. Basically, this is the data set that I'm having. So df is equal to pd.readcsv of, I'm passing this parameters, which is basically data.csv names is equal to column names. So data.csv, I already have that in my folder. So the folder is basically bits folder. So if you just check the present working directory, you'll be able to see what is that folder that I'm using. All right. So serial is nothing but the number of rows, and then we have the date, age, distance, stores, latitude, longitude, price. So which is a target variable here? The price is a target variable. What we need to consider now, we'll have to exclude the serial, and then we'll have to consider this date, age, distance, and then stores, latitude, and longitude. And all these variables are having different values here. It ranges from different values. Like for date, we have 2009, 7, something like that. And then age, 21, 14, and the distance is having some range of values. Latitude and longitude is having some range of values. So whenever you have such a kind of values, the thing is normalization is very important. That is one thing that you'll have to, do it. So basically that we do it by taking some of the methods here. I'll show it how we actually do it. What I'm trying to do it here is, it's good practice to check if the data has any missing values. In the real world, this is quite common, and must be taken care of before any data processing or model training. Remember, missing data, if you have the missing data and if you're training with the missing data, then you'll end up with the bad model, right? So the thing is, I'm using this functions like isNA, not a number, and then dot sum. Basically, it says that 0. You can also use isNull, as I used in the previous example. Even that functions can be used. So the thing is, you'll have to remember some of the functions just to go with the things like this. All right. Now coming to this one, after running this, we have this one, latitude, longitude, all are basically 0. It means that no missing values are actually present. All are integer, 64 bits. All right. And then coming to this, df is basically the variable that I've taken. Df is equal to df dot ilog. So ilog, log are all basically this, slicing functions that we are making use. So we know that df is basically the data frame. So once you read this data frame, okay, so now it is actually stored in this df. When you use this df dot head, it will show the first 5 rows that you are actually seeing here. All right. And then once you use this df.ilog is basically you're accessing this column data in the column wise. If you're using this only log, basically it is row wise. Okay, you'll have to look into the documentation of pandas data frame, which is very important. So I'm using this slicing operator here, colon, comma, 1 colon. What does it mean? Actually, this is basically says that rows. Consider all the rows. How many rows do I have? 5,000 rows into 7 columns, isn't it? So from 0 to 4,999, comma, and then leave that first column, which is serial, and then consider all the columns from there, right? So that is why I'm accessing, leaving that serial, date, age, distance, store, and then latitude, longitude, and then price. All right. And then finally, so this is what I'm trying to do here. Data normalization is very important. We make it easier for optimization algorithm to find minimas by normalizing the data before training the model. We'll have to normalize the data because the values are ranging from different values, right? So it is scattered like that. We'll have to bring the values in between the two range, right? So we are trying to bring that values now. So for that, I'm trying to take a variable called df underscore norm, which is equal to df, which is basically this one, df minus df dot mean. I'm actually considering the mean of all the columns and then divided by the standard deviations, df dot standard deviations. And if you see the end of it, you can see the values are actually ranging from negative to positive values. All right. And then if you just run this one, so you get these values. Okay, so this is the one that you'll have to do it before you actually train any model. Okay, and then convert label value, which is a label now. Price is basically the label that we have taken off, and then y mean and then y standard. If you see that y, it is basically the dependent variable, which is the target concept, right? So I'm taking this y mean and then y standard variable. Y mean is basically equal to df of price dot mean and then df of price dot standard deviation. I'm making use of the original data frame, which is df. I'm not using this df norm. Just understand that price dot mean, price dot standard values. I'm just storing those values in y mean and y standard. Okay, and I'm actually considering one function in Python which is define convert label value of predictions. Why it is required to convert this label value? Just read all the sentence that I have written here. Because we are using normalized value for the labels, we will get the predictions back from a trained model in the same distributions. Whenever you try to predict something using this model, at the end, you will get the same normalized value. So if you wanted to get the original value, something like this without the normalized one, okay, so for that we'll have to convert back to the actual data, right? So for that, what we do is that we take this function here. So back from a trained model in the same distribution, previously the original one. So we need to convert the predicted values back to the original distributions if you want predicted values. All right. So the model will output the normalized value. We'll have to convert back to the same distribution as in the original data set, right? For that, I'm taking this particular function, convert label value. The predicted value will be passed here. That is a parameter I'm considering here. And I'm trying to return, I'm doing this explicit conversion. Basically, I'm trying to return integer values here. So int of predicted, prediction, the same variable, and then into y standard plus y mean. You'll have to take this y mean and then y standard, right? And then just to say the conversion, check the conversion. What I've done is that I've taken this print of convert underscore label of value. I'm passing this predicted value, which is 0. I request the participant to mute your audios. All right. So print of convert label, I'm calling this particular function convert label value, and then I'm passing a sample value, predicted value. This is basically the normalized one. This is not the original distribution, isn't it? 0.350088. That is basically the normalized one. If you just pass this, call this function, and then if you just compute this one, and you would get is 40,263 as the original distribution, just to check that whether I'm getting or not, right? So that is what I'm trying to do it here in this convert label concept here. So moving on to the next one. So create training and test set. So how do you create the training and test set? You'll have to make use of DF norm. You should not use DF. You will have to use normalized data here. So you'll have to have this X part. You'll have to have the Y part. X part and the Y part. Now, how do you consider the X part? Remember, X part is basically the independent variable, which will not have this dependent variable, which is Y. All right, so that is why I'm using this df normalized dot ilog function and then slicing that. Consider all the rows, putting this colon, comma, colon 6. It's nothing but 6 columns you'll have to consider, excluding that particular the price column, right? And then if you check the head of that X, and you would get something like this. First 5 rows, which is date, age, distance, stores, and then latitude and then latitude. All right, and then we have this y, which is basically this y is equal to df norm dot ilog of colon comma -1. It is saying that consider all the rows, okay, with only the last column. Basically, it says that you're considering only price here. So if you just execute this one, so you see that the price, okay, which is basically the float 64. All right, and then coming to these features. Okay, we will need to extract just the numeric values for the features, and labels as a TensorFlow model will accept just numeric values as input. Just remember this concept now. All right, now what I've done is that I've taken x underscore array, y underscore array, and then if you just use this standard variable, which is x dot values, remember here I'm using this variable x here, the same y and the x. I'm using this x dot values, y dot values. Tensor itself says that it is an array, series of elements. or items, all right? And then I'm trying to print that X array dot shape and then Y array dot shape, you would get something like this. So X is basically the independent. How many independent variables do you have? So it is dependent on the longitude, latitude, and then stores, and then the number of bedrooms, etc. 5000,6, right? So the number of columns, this X underscore array is having 5000 rows and then 6 columns, and then Y underscore array is having only 5000 rows, and then this is basically the single dimension, which is only 1 column, which is Y. All right. Okay. Now we'll have to do this train and split part. So we'll keep some part of the data aside as test set, that is unseen data. Okay, out of that 5000 rows, we'll have to keep some rows as the test data and then many rows as train data. Just remember the concept of the theoretical concept that I had explained. You'll have to split that into train and the test plot, right? So test set you'll have to consider and remaining will be the train part. Now let's imagine that you're actually splitting that into X train, X test, Y train, Y test, all right, which is equal to something like train test split function. You're passing X array, Y array, and then test size is equal to 0.05, shuffle is equal to true, and then random state is equal to 0. So I'm putting random state is equal to 0, shuffle is equal to true. So shuffle is equal to true means what? You're actually shuffling the data. Let me try to annotate this part. So how actually dividing this part, that's very important. Let me try to go with this annotation part. Okay, this is happening something like this. Imagine that, excuse me. Okay, so imagine that you have a data set something like this. All right, so this is basically the Y part. Okay, and all these are basically the X part. Okay, and then what I'm trying to do is that I'm considering some part as X underscore test. Okay, this part, minimum part is X test, also called as unseen data. Okay, and this part, the last column, is basically the Y test. Okay, and then this maximum part is basically this X train. Okay, and then this part is basically the Y train. So this X and then Y are now being divided into X train and then Y train, X test, and then the Y test. All right. Okay, once we are done with that, so I think the 50%, like 0.05%, I'm taking it as the test size. Remaining will be your train part. Let me clear this part down. This is how we actually divide the things, and you're trying to see the shape of it. Shape will give us the number of rows and the number of columns we are actually considering here. 4750 is basically the X train shape, comma, number of columns is basically 6, and then Y train is 4750. Out of 5000, I'm considering 4750 as the train part, and remaining are basically the test part, and 250 are basically the X test and the Y test. It means that how do you evaluate a model? So you will have to pass this X test to your model. Okay, and then it has to predict the Y test. So this is basically the actual one. Okay, and then your model will predict something. We need to compare this predicted one with the actual Y test. Okay, if this is correct, if this is nearly 85% accuracy and 95% accuracy, then your model is really good model. In that way, you'll have to do the things or evaluate the model, right? So this is how we actually divide the things. So let me quickly run this one. All right. Okay, so done with running of this particular program. Okay, now the thing is you'll have to create the model. This is basically the sequential model, the neural network, the dense neural network that I'm creating. Define get model. The function name is get model, and model is equal to sequential. And then I'm taking this different layers of neurons. The first layer is having 20 neurons, and second layer is having 20 neurons, and the input size is 6. Basically the input shape is basically six columns you are passing. Comma activation function is ReLU activation function. This is very important to understand. Rectified linear unit. So there are so many activation functions if you wanted to activate any neurons. All right. So rectified linear unit, sigmoid equations, tan H, ReLU. So you'll have to look into the documentation of ReLU. All right. So that's basically says that if the value is below 0, then it will always return 1 x, and then if it is always 1, it is 1, something like that. Please look into the documentation of ReLU in the Wikipedia page. You will get all the documentation. All right. So the activation function that I'm using is basically the ReLU, something like this. Okay. The output 1 is basically the 1 neuron. So this is what the price neuron. Okay. All this, it is taking the different the variables, the independent variables. And then, okay, let me try to clear this part. And then we have this model.compile. So the loss metrics that I'm using here, this is basically the linear regression. So mean square error I'm using. So which is, I say that MSE is equal to loss is equal to MSE. And then optimizer, what is this optimizer? This is basically very important one. If you just heard about this gradient descent in linear what is it, neural network, you'll have to understand the advancement of this gradient distance, which is ADA delta. Okay, please look into the documentation. This is basically the optimizer. Why we are using this optimizer? You'll have to optimize your neural network. It means that, so you'll have to you'll have to set your weights, and then learning rate. You'll have to learning rate of your neural network. Okay, the thing is, for the first iteration, in the first iteration, you see you're not expecting the actual output. You go back to that, and then you actually optimize your algorithm. Okay, optimization is done using this particular algorithm, which is ADA delta. We also have this ADAM optimizer, and then gradient descent optimizer. There are so many optimizers. Please look into the optimizer concept. Basically, the optimizer will actually optimize your neural network. It means that it will always reassign or try to put some different values for the weights and the learning rate. Okay, learning rate basically says that, so how fast your neural network is actually learning. You'll have to either increase the learning rate, or you'll have to decrease the learning rate, or you'll have to have the optimal learning rate. So that is done by this ADA delta. All right. So and then we have this written the model here. Model is equal to model. Okay, model is going to get model, and finally I'm actually going with this summary. So let me quickly run this one. So we are at the end of this particular one. So let me quickly run this one. So you would get something like this: dense 9, dense 10. This is basically the sequential model, and the parameters it is considering is 70, 220, and then 105 and the 6. So the thing is, parameters are basically the values that it is considering in any iterations. Total parameters is basically 401, and trainable parameters is basically the 401. Okay, that is basically the summary that we are actually trying to consider. All right, now coming to this early stopping, I told you that in the beginning there is something called as what is it here, the early stopping callback. What are actually callback? Doing callback. What do you mean by callback here? See, the thing is, whenever you actually start training a model, okay, it starts learning by itself. The thing is, at some point of time, you'll have to stop that training. How do you actually stop the training? You'll have to make use of some functions like early stopping, which is what we call it as a callback from Keras to stop the model training. If the validation loss stops decreasing for a few epochs. Epochs is basically the term that is used for iterations. How many times you are going and coming up and down of your particular model and then training your model. All right, validation loss is nothing but what is a loss? Basically the difference, right, you are getting in each iterations. All right, so the thing is, when the validation loss is less, you would ask your model to stop training itself. All right, that is what we call it as the early stopping. And then early stopping monitor value loss, and then patience is equal to 5. So we have some parameters here, so please look into the documentation. And then model is equal to get model, and then predictions on untrained. So what we need to pass, as I told you, that you'll have to pass this X test, and then you would get prediction, and then that prediction must be compared with Y test, isn't it? So that is what we are trying to do here. We are going to finally fit the model here. How do you fit the model? Of course, you'll have to pass this X train and the Y train. You are not going to pass this X test and the Y test, but you'll have to pass X train and the Y test, and then the validation data will always be your X test and the Y test. Just remember that. And the epochs, number of iterations, top to bottom that I am running is 1000 iterations, and then callback is basically the early stopping. Early stopping says that when the loss is very less, you just stop training your model. That's it. Okay, so just run this particular model and then it starts learning by itself. As you can see here, so you can see the loss here, value loss, and then you can also see the iterations, epochs, 18, 20, something like that. It keeps on going like that. Okay, and then finally, when the model is been trained, when the neural network model has been trained, you'll have to see this particular what is it, the graph. I have to plotted this particular graph. The blue line says it is a validation loss and the training loss. As the training goes, or the number of epochs is going, okay, the validation loss is also decreasing, right? And the training loss also is decreasing. That's what we see it in this particular graph, loss in the y-axis and the epochs in the x-axis. All right, and then we have this predictions. Okay, this is the final prediction that is actually running. I cannot stop. You can also stop, forcefully stop it, but it is actually running here. I'm still in the 64. It has to complete 1000 epochs. Okay, it is still going. You let it run. Okay, and then finally compare the predictions. What you're actually doing it here, you'll have to predict on train. That is a variable that I've taken. Model, that is a model that you have done. Okay, model dot predict of what you're actually passing. X test you'll have to pass. Just remember, you will have to pass X test and you're getting some predictions, right? So what you're actually comparing here, compare predictions on untrained, okay, comma predictions on trained, comma y test. You're passing this to this compare prediction function that I created here, basically. All right. Okay. So that's basically does something like this. This is untrained model. The thing is, before actually train the model, okay, this is basically the line that you're seeing. So red line, red dots are basically the untrained observations. And then the trained one is basically the green one. It is aligning to that particular line to some extent after you actually train the model, right? So, and then finally, this one, converting that, the plot for price predictions and then raw predictions will look the same with just one difference. The X and Y axis scale is changed. The X and Y axis actually is changed now. This is basically -1, -2 for this normalized one. For this, the actual distributions, we see something like this. So this is basically the compare predictions, price on untrained, comma price on trained, and then Y price Y test. So basically this is the green points are the predicted one or the model one. The red points are basically the untrained model. Okay, the model, my model is still running. Actually, it will take some time. This is basically the small data set. Just imagine that if you're taking a really big data set, how much time does it take to run, isn't it? So that is what this algorithm is all about. It's taking time, maybe, yeah, it is 414, 417 epochs still running. So that's it for this session. Thanks very much. I hope everybody is clear with the session. I think it is already 6, right? Let me stop this one. Okay, so yeah, I think I'm done with the explanation of this TensorFlow networks.
Thank you so much, sir, for your wonderful session. The 3 hours of your session was fantastic, Hemant, sir.
Thank you very much, ma'am. Pleasure doing it.
And thank you for accepting our invitation in spite of your busy schedule. Thanks a lot, sir.
Yeah, thank you.
Participants, if you have any queries, you can please.
I expect any queries. If you have any queries, you can just mail me. Otherwise, you can call me at any point of time. I'll be happy to answer all your questions. I think given this time limit, I've tried covering this concepts, right? So it will take nearly 1 week or 1 month to go with all this different machine learning concepts, right? So and then I thank Bits for giving me this wonderful opportunity to deliver this webinar, right? International webinar, data science, and then the future, which is the technology, right? Thanks very much.
Thank you so much, sir. Can we have a photo session now? Please on your video, sir. Participants, please on your video for the photo session. Ramakant sir and Abhinav, you can please take that. I hope it's done. Yes. Thank you. Thank you so much, Hemant sir. Once again, thank you.
Thank you. Thank you all. I hope you have enjoyed the session. Thanks very much for joining the session. Thanks very much.
Yes.
Take
Yes,
care.
sir.
Bye-bye. Bye-bye.
So, my dear participants, thank you all. The feedback link and the day 4 quiz will be posted on chat box, YouTube and Telegram. Your feedback is so valuable. And tomorrow we have another interesting session by Dr. Venkateshwara Rao sir on neural networks and natural language processing. Thank you. Srinivas sir, over to you.
Madam.
Yes, sir. We can end the session.
Parvesh sir. Parvesh sir. Okay. All my dear participants, please complete the feedback form, and as early as possible you finish it and submit the form, and quiz also as early as possible. And tomorrow is the final day, and we have 2 sessions by Dr. Venkateshwara sir. He's from NIT Warangal. You can enjoy the session, and at 6:30 we have valedictory ceremony also. So please all the complete all the quizzes and feedback forms. Thank you. Jaya madam, you can end the session.
Yes, sir. Thank you. Thank you all. Good night.